So good evening everyone. Today I'm going to discuss about the topic pulse code modulation. It is my next video and I'm Arijit Sinha Mahapatra. I'm from Kochiba Government Engineering College and I'm studying in third year of PC department, and today our topic is pulse code modulation or PCM. So in the first slide we can see here the pulse code modulation introduction and definition. In the introduction we can see pulse code modulation is the name given to the class or baseband signals obtained from the quantized PAM or pulse amplitude modulated signals by encoding each quantized sample into a digital word for baseband transmission. The code word bits are transferred to pulse waveforms. The definition of pulse code modulation is known as digital pulse modulation technique. In fact, pulse code modulation PCM is quite complex compared to the analog pulse modulation technique like PAM, PWM, or PPM, in the sense that the message signal is subjected to a great numbers of operations when pulse modulation is applied to a binary symbol. The resulting binary waveform is called a pulse code modulation waveform. Key idea: the core concept of converting continuous time varying signal into a digital sequence that can be easily stored in memory devices, processed using computers or digital signals processors, transmitted over long distances without significant degeneration from noise. Advantages of PCM are high noise immunity, easy to process, secure, and lastly it is compatible with digital switching and network. Now the block diagram of PCM. So in the first block we can see analog message signal. It is passed on to the next block, low pass filter or anti-aliasing filter, which is passed on to the next block, sampling. After that, quantizer. Then it is passed on to the binary encoder. Then by parallel to serial converter, it passed to the channel. After that is passed to the serial to analog converter, and then to the decoder, and then it is passed to reconstruction filter and reconstruction signal. There are three fundamental steps in PCM. They are mainly sampling, quantization, and encoding. So the need for PCM's fundamental steps: there are infinite members of amplitudes in continuous amplitude and continuous time sequence. There is no such time interval where the amplitude of signal is defined. Since time is continuous, it is due to three reasons. We have to convert continuous time amplitude into discrete amplitude, discrete time. So in the sampling, you can say the graphs. The first graph is amplitude versus time graph, and the second graph is amplitude versus n graph. Output is only available in integer multiple of ts. Since ts is constant, so the time axis of discrete time has variable n. Next, to the quantization, to discretize the amplitude, we use quantizer, which means each sample to nearest available level or quantized level. The more is the quantization level, more is the accuracy of the signal. Quantizer can be broadly classified into two categories. First is uniform quantizer and the second is non-uniform quantizer. And you can see here the quantizer is divided into two subcategories: uniform quantizer and non-uniform quantizer. And the uniform quantizer is further divided into mid-rise and mid-range. So here is two graphs. The first graph is mid-trend and the second graph is mid-rise. You can easily distinguish the two parts using these graphs. Next, the encoder. Encoder is a block that converts the quantized values into a binary code for digital transmission of storage. Each quantized level is assigned a unique binary number, which represents the amplitude level. So the signal first travels to the sampler, then to the quantizer, then the encoder. In the next slide, here is the level of quantizer. If a quantizer has 4 levels, encoder needs 2 bits for each level. If a quantizer has 10 levels, encoder needs 4 bits for each level. So number of bits needed is log base 2 L, where L is the level of quantizer. So quantization noise, the difference between actual sampled value and the quantized value is called quantization noise. So you can see in the formula, E is termed as quantization noise, XQ NTS is quantized sample, and X into NTS is original sample. The difference between these two is the quantization noise, which is termed as E. quantization step size. So in the graph you can see the maximum amplitude in the plus zone is plus x cube plus xm, and the minimum amplitude is minus xm. So the maximum signal amplitude plus xm, minimum signal amplitude is minus xm, and the step size delta is 2xm by q. Here 2xm is peak to peak amplitude, q is the number of levels. So therefore maximum quantization error E max is mod value of delta by 2. Uniform distribution of quantization errors. For uniform quantization error is uniformly distributed in range minus del by 2 less equal to error less equal to plus del by 2. So the range of the error is from minus del by 2 to plus del by 2. Then the noise power v square noise is equal to the integration of error square. So the integral from minus infinity to plus infinity e square function of e d, assuming error is uniformly distributed. So the noise b square noise is equal to delta square by 12. Signal to quantization noise power ratio SQNR is signal power by quantization noise power. Signal power is termed as P, and the quantization noise power is delta square by 12. So the SQNR is P by delta square by 12. The step size delta is equal to 2xm by q, and putting the value in SQN in the equation, we can say the SQNR is P by 2xm by q whole square by 12, which is 3pq square by x square m. So the SQNR is 3pq square by x square m. It is very important. Next to the SQNR in terms of bits, for q is equal to 2 to the power v, SQNR is 3 into p into 2 to the power 2v by x square m. For normalized condition where xm is equal to 1 and p less than equal to 1, xqnr is 3 into xqnr is 3.2 to the power 12. And if we turn the SQNR in terms of decibel, we can say XQNR in terms of decibel is 10 into log 10 base 3.2 to the power V, which is near equal to 4.8 plus 6V. So here is the end of our video. Thank you.